This is Mr. Lee's physics class. I'm Mr. Lee. In this video, we will talk more about the designs of liquid in-glass thermometers and the reasons behind these designs. We'll also touch a bit other types of thermometers. There are two common types of liquid in-glass thermometers, alcohol in-glass and mercury in-glass thermometers. It's obvious from their names that the liquids they use are alcohol and mercury respectively. You may wonder, why these two liquids? Can it be water? Water is cheaper and can be found everywhere. So why don't people just use water in the thermometer? Your first thought may be that water is colorless and is inconvenient, but it turns out that alcohol is also colorless. The usual red color of the alcohol is not its original color. It is due to the dye added to the alcohol to make it more visible. So, back to the original issue. Why isn't water used? Give you a hint. It has to do with how water expands and contracts when its temperature changes. I will not disclose the answer here. Go search for it on your own. There are several designs about a liquid in-glass thermometer you should note. First, the bulb at the bottom is usually large so that it contains a lot of liquid inside. To understand the reason for this design, you need to first have some common senses about thermal expansion. When something is heated up by a certain temperature, its volume typically expands by a certain percentage. For example, the volume of ethanol, a common type of alcohol, expands by 0.11% for every degree Celsius rise in temperature. Since it is the percentage volume increase which is fixed for every degree Celsius of temperature rise, having more liquid stored in the bulb will give a greater actual volume increase and therefore more increase in the liquid length per degree Celsius of temperature rise. To conclude, a larger bulb can increase the sensitivity of a liquid in-glass thermometer. Second, the capillary tube is usually very narrow. Along with a large bulb, this also increases the sensitivity of a thermometer. I'm not telling you why for now. Think about this first and we'll discuss this later. So far, we have been discussing the designs of a liquid in-glass thermometer around increasing its sensitivity. But there are other aspects of a thermometer besides sensitivity. For example, how immediate it responds to a temperature change. Make sure that you distinguish this from sensitivity. Sensitivity is about how much response, that is, length increase, for a certain temperature rise. But even if its length increases a lot for a tiny temperature change, you could still have to wait a long time for that to take place. What I mean is, how much the thermometer responds and how fast it responds are two totally different aspects. And of course, generally speaking, we want a thermometer to respond fast. To do this, the glass wall of the bulb should be thin. The point is, the bulb of a thermometer is where it actually detects temperature. If its wall is too thick, it will take a long time for any temperature changes in the outside environment to affect the liquid inside the bulb and thus making the thermometers respond slowly. To conclude, thin glass wall around the bulb allows the thermometer to respond fast. So much for the discussion of liquid in-glass thermometers. I want to remind you that there are a lot of other types of thermometers, but whatever the types, they all have properties which change with temperature and which can be observed. The idea is that temperature cannot be seen, but say if the color of a substance changes with temperature and now you see that its color changes, then you know the temperature must have changed. We call such properties of substances which change with temperature the temperature-dependent properties or the thermometric properties. Using liquid in-glass thermometer as an example, the temperature-dependent property it uses is the volume of a liquid because the volume of a liquid changes with temperature. This table here shows some thermometers and their corresponding temperature-dependent properties. Some major applications are also stated. You don't have to remember them all, but at least you should know the temperature-dependent properties that they rely on to measure temperature. Also, you should have a general sense of how these properties relate to the application of the corresponding thermometers.